Welcome to the nature of things. I'm David Suzuki. They once dominated the planet. They ruled the land in an incredible array of sizes and shapes for millions of years. Then suddenly, they were gone. Tonight, the fascinating puzzle of the dinosaurs. A place like this is a part of history, the ancient history of the planet. This is a bald cypress swamp in southern Florida, a rich habitat for life that survived hundreds of years. Some of the trees here were already old when Columbus first landed in North America. But that's just a small way back. 70 million years ago, parts of southern Alberta were much like this. Some of the trees, plants, and animals have scarcely changed over thousands of millennia. But something's missing. If this really were an ancient Alberta swamp, I'd be looking nervously over my shoulder, listening for something crashing through the foliage. Patterns of growth and change. The world is a living web of relationships, made and unmade by time. Every new life is part of an ancient, evolving community. As we put together a picture of the world we too are part of, we begin to understand the forces that gave it shape, how it came to be as it is. We see the logic of a bird's wing, purpose in the symmetry of a palm. Then, we can move out of our present moment and recreate a world that's vanished, the living world of the dinosaurs. These splendid reptiles catch the imagination as we reconstruct the patterns of their lives. Giant duckbills feeding their young in the nest, or moving through the swamps of ancient Alberta. Their shapes are endlessly diverse and yet somehow familiar. This race of dinosaurs creates lifelong enthusiasts like Dale Russell from Ottawa's National Museum of Natural Sciences.
There are dinosaurs that are built along the lines of ostriches, obviously called ostrich dinosaurs, that have secondary palates in their skulls and beaks like birds. They look extremely avian in their cranial proportions, and I suppose they were insectivorous or ate small lizards and things like ostriches do today. Then we have our old friends, the brontosaurs, which always excite me. They're such wonderful creatures with such heavy, ponderous legs and such inflated, interesting-looking axial skeletons. The backbones and skulls are always interesting of sauropods, and I look upon them as gigantic vacuum cleaners wandering on the surface of the land, moving their necks slowly around, cropping vegetation over a 30 or 40-foot radius in some cases, and conserving energy, and behaving essentially like turtles. Dinosaurs are such strange mixtures of shapes. I think of tyrannosaurs, which were horrible creatures. I just don't like to think of tyrannosaurs living, or at least me in proximity to living tyrannosaurs. I'm sure the situation would be very unstable. They have a wart-like knobs on their noses. They have a gigantic wolf-like head on their bipedal creatures, something like a Australian emu or something like that. So they're an unlikely combination of characters that sort of piques one's interest in or makes the world seem so much more exotic than. There are other kinds of dinosaurs. There's enough variety of dinosaurs to keep one very happy from a morphologic point of view.
Why are we all so fascinated with dinosaurs? I think partly it's because of their size. Many of them were huge and scary. Monsters. We all like monsters. And part of it is the mystery. They were enormously successful for a very long time. The great reptiles covered the land and penetrated the seas and the skies, yet they vanished. Why? But most of all, dinosaurs give us scope for wonder and imagination. I mean, we have very real, tangible evidence that they existed. There are fragments of fossil bones everywhere, but we have to piece together the clues and try to imagine what they were like and how they lived. It's the best kind of scientific puzzle, and this is the best place to begin, at Alberta's Dinosaur Provincial Park. The Red Deer River has carved a window in the prairie. Looking through it, we can see the distant past. Wind and water sculpted this unique landscape. Time has contracted here. Living animals today move among the scattered remnants of life from 75 million years ago. This old planet of ours has seen a lot of life in its time. In Dinosaur Provincial Park, the bones are showing through. Collections of fossils are found in bone beds all over the park. For paleontologists like Phil Curry of Alberta's Tyrrell Museum, the smallest fragments have a story to tell.
Many of the bone beds in Dinosaur Provincial Park also include what we call microvertebrate sites. And microvertebrate sites are just areas where we find large numbers of small fish scales, mammal jaws, lizard jaws, and a variety of small bones that give us an idea of the kinds of animals that were running around when the dinosaurs were here. For example, in the space of 5 minutes, we've picked up some fish scales, parts of 2 teeth of a large carnivorous dinosaur like Tyrannosaurus rex, a duck-billed dinosaur tooth, a ceratopsian or horned dinosaur tooth, a crocodile tooth, pieces of turtle shell, Champsosaur vertebrae, and Champsosaurs were a small crocodile-like animal that lived in the water, and various fragments of bones of dinosaurs.
Larger bones, like these vertebrae, weather out in the rain. Sometimes part or all of the rest of the skeleton lies behind them in the rock. Carefully excavated, pieced together, and mounted in the museum, this fossil framework builds an animal. And from this, we can start to reconstruct the details of its life. In the gallery at the Royal Ontario Museum in Toronto, curator Chris McGowan.
Now this dinosaur that's terrorizing me at the moment is Allosaurus. He was a meat eater, which is very obvious when you think about it. Just take a look at these teeth. We see they're all sharp, sharply pointed teeth, and they've got serrated edges. If I run my finger along here, I can feel those serrations just like a steak knife, which is very good for puncturing and for slicing through meat. Another thing about this guy is his jaw joint. If I was brave enough when he was alive to grab him by the chin and try and waggle the chin from side to side, I'd find that it wouldn't work. Mine goes from side to side, his doesn't. His doesn't because of the sort of jaw joint he's got. He's got a jaw joint that only allows an up and down movement, which is very good for slicing. You know what it's like when you've got a pair of scissors, they've got a wonky joint here, and they waggle from side to side. You try cutting paper and it goes every which way. Not with this one. Up and down for slicing. Very effective for slicing meat away from bone. So this is the good equipment for dealing with the meal once you've got it. But of course you've first got to catch the meal. And this is where this equipment comes in handy. You can't help noticing these very sharp claws on this guy. He's got sharp claws on the hand. He's also got very sharp claws on the feet. And we can visualize this very fine beast grabbing hold of its unfortunate victim and kicking and slashing with those sharp toes and doing an untold amount of mischief, which is what a carnivore needs to do because it's got to get the job over quickly.
Any animal survives by conserving energy. Getting the meal must use less energy than eating it will provide. The cheetah is built for speed. It's the fastest of all the modern carnivores. Its backbone acts like a spring, providing short bursts of incredible acceleration. But with its light, streamlined frame, it can take on only small prey, no larger than itself. The kill must be quick, or the cheetah risks injury. If it's put out of commission, a carnivore starves. Cheetah or dinosaur.
The picture that we've made up of this dinosaur here is one of an animal that is a hunter, going after its prey, killing its prey and eating it. But it might not have done that. For some people, these guys, Allosaurus and animals like it, were scavengers, just going and eating up dead things on the ground. Quite unsavory, really, isn't it? So there is possibility that this wasn't the great active predator, and this is what we've always got to remember. We're talking about things that were been dead 120 million years. We can't know for sure what their lifestyle was. Just the same in present-day situations. If, for example, we look at the skeleton of a hippo, there's no clue in that skeleton to tell us that that animal spends most of its life in the water. It's an aquatic animal. But we don't know that just by looking at the skeleton. So we've got to be very circumspect when we're trying to recreate lifestyles of things that have been extinct all of these years.
What the bony anatomy can't tell us, other clues may. Evidence left by the animal's behavior in life. When the hippo goes ashore to forage, it leaves its mark, footprints driven deeply into the muddy bank. They'd tell us a lot about the hippo if it wasn't there to be observed. From them, and similar footprints on the riverbed, we might even deduce an aquatic life. Like the hippos, living dinosaurs left their mark on the world. They didn't simply disappear without a trace. Footprints, frozen in time. Dinosaur trackways are rich sources of information about the animals that made them and about their social behavior. Many have been found, and some have been lost again. The Peace River Canyon in British Columbia was flooded in 1979 for a hydro project. Only a few of the large number of dinosaur prints could be saved in 4 seasons of hard work before the dam was finished. Casts of some were made by spreading resin on soft fiberglass packed into the imprint. A record of the living weight of bone and muscle that once passed by. Other footprints were hammered out of the rock and taken to the Tyrrell Museum. Phil Curry directed the project.
This is one of the many footprints brought back to the Tyrrell Museum of Paleontology from the Peace River Canyon. And it was made by a duck-billed dinosaur that at the time was probably swimming in the water and occasionally putting his foot down into the soft mud beneath the water itself. Now we can learn a great deal from dinosaur footprints that we just can't learn from the bones, simply because the bones are a representation of dead animals, whereas the footprints were made while the animal was still alive and record what the animal was doing while it was alive. In addition to that, footprints can give us a lot of information on the soft anatomy. For example, we know that from footprints, duck-billed dinosaurs had webbed toes. If we look at the skeletons of duck-billed dinosaurs, we can see that there were bones running through this region in each of the toes, and that there were large pads underneath each of those bones. However, there is no evidence in the skeleton that there was any kind of a heel structure in the bones themselves, although there was a large fleshy pad at the back of the foot.
This dinosaur is a herbivore, a plant eater. But how do we know that it actually stood and walked in this posture. We can be pretty sure about this specimen because we've actually mounted it in a real dinosaur trackway. Down here are the imprints that a dinosaur made about 70 million years ago in Alberta. And we see the toes fitting in the outline of this footprint. You notice with this skeleton, as with just about all dinosaurs, that the back legs are considerably larger bones than the front legs. They're much more heavily built, they're much longer, and the reason for this is that they're the ones that are bearing most of the weight.
Quite a lot of weight at that. The duckbill was about the size of an elephant. In the fight against gravity, all terrestrial animals must reach a compromise between stability and speed. The elephant has opted for size and stability. It moves out of the vertical slowly and deliberately to minimize stress on its leg bones. The largest land mammal alive, it's safe from predators, and it doesn't have to chase its food, so speed is unnecessary. But compared with dinosaurs, the elephant is almost dainty. A browsing sauropod weighed as much as a herd of elephants, and the great tyrannosaurs were at least this elephant's size. In that world of giants, a harmless herbivore like the duckbill had to be big and fast as well.
This dinosaur, Lambeosaurus, which is a duck-billed dinosaur, was a plant eater. And like all plant eaters, it had a large gut. The plant eaters need a large gut because vegetable matter takes a long time to digest. You think about a cow, enormous, great, broad animal, and we can get a pretty good idea of the size of this animal's gut by looking at the body outline. Look at this bone here and follow along a line down at about its knee level into here. And we can visualize that one great big mass swinging like a pendulum between its legs as it walked, a large gut. Fairly heavy-bodied animal. Front end of the body, very heavy, and being counterbalanced by the long tail. It's doing a balancing act. So we have all of the weight concentrated right here at the hip joint. And the animal balances on its back legs like a teeter-totter through that hip joint.
We see the same remarkable balancing act in some animals alive today. Like the duckbill dinosaur, the kangaroo holds its backbone horizontally as it moves at speed on two powerful back legs. Front legs tucked up, the duckbill used its tail like this to maintain stability as the center of gravity shifts. But the duckbill didn't hop. It strode like the ostrich, poised on the fulcrum of its pelvis. Those long slanting leg bones are built for speed, leaving the hip joint at an angle to provide powerful takeoff momentum. How fast an animal can run is suggested by its anatomy. One important clue is the relative length of its lower leg bones. They're very long in the horse, which achieves greater speed than the duckbill could with its broad bovine body. We can picture the duck-billed dinosaur living like the grazing animals of today. Moving in herds, they crop the vegetation and ground it down with hundreds of teeth that continually replace themselves. When the duckbill was alive, there would have been a far greater density of animals than on the African plains today. Thousands and thousands of large reptiles, making lasting impressions on the world they lived in. These incredible formations are all made of sand. and the sand grains in them have made a remarkable journey. Over hundreds of kilometers through millions of years. Almost 100 million years ago, this sand was part of the Rocky Mountains when they heaved up out of the plains. Rivers then brought the sand here, where it cemented into sandstone over the millennia. Now it's moving again, eroded out of the hillsides by rain, which then washes the sand down through the gullies into the Red Deer River. The vast changes that take place on the Earth's surface are written here in sand. And as we read the record, we begin to recreate the vanished world of dinosaurs. Dinosaur Provincial Park is part of a deep trench cut in the prairie surface, the valley of the Red Deer River in southeastern Alberta. About 15,000 years ago, as the last ice age retreated, water from melting ice sheets made this scar. It exposed a far more ancient chapter in Earth's history, sediment from 75 million years ago. When that sediment was laid down, Saskatchewan was underwater, a shallow sea stretching all the way up from the Gulf of Mexico. On its western shore, this part of Alberta was a coastal plain, crisscrossed by rivers draining out of the Rocky Mountains, a rich habitat for countless dinosaurs. As the silt-laden rivers built the land, millions of bones were preserved in the sediment. Today, the Red Deer River and its tributaries are eroding the land, and the history of that ancient delta is coming out again into the sunlight. The way water alters the face of the earth hasn't changed. These modern rivers can teach us what was happening here when instead of a deer, a dinosaur might have walked through the water. Geologist Emlyn Coster.
We're standing here on the bank of Little Sandhill Creek, which is one of the main drainage systems to emerge from the Badlands and is responsible for the erosion of the Badlands. This creek flows in this direction here and within 100 meters meets the Red Deer River further on downstream. The creek is here taking on an abrupt bend to the left. This is then a meander bend where there's quite a contrast in the processes happening on the outside bank and the inside bank. Over there, the outside bend of this meander is showing lots of signs of erosion with the sloughing off of blocks of the bank material. And on the inside bend of this meander, evidence of a lot of build-up and deposition of the sand. So the result of this erosion on the outside bank and deposition on the inside bank through time is that the course of the creek will move over in that direction and leave behind it the point bar. Yesterday's rainfall caused the stream to rise to about this level above the bed, and at that time the sediment, the sand, was being transported along the bed and has now left for our view, now that the creek level has dropped, this sequence of ripple structures. The individual ripples have a shape which is nicely demonstrated by this one here, where there is a long, low upstream sloping side and a steep downstream side. And the division between those two sides marks the crest line of the ripple. Now that's the result of the sand grains being moved up here and then free falling down this downstream side. The result of that is that the crest of the ripple, of each ripple, moves downstream with time. And the result of all these crests moving downstream is that inside this structure there are a series of sloping layers like this. And this structure is what we see preserved in the sediments of 75 million years ago, the ones that contain the dinosaurs. Well, there are structures here which very closely resemble the ripples that we've seen in the modern creek bed that tell me about the direction and the manner in which the sediment was transported by this ancient river. And as the ripple moves downstream with more and more sediment being added to it, there are a series of inclined layers, and we see those very well preserved here. And this information is very useful to us because it's these sedimentary rock layers with these transport directions that contain as fossils the remains of the life at the time. So this information then helps us to understand the conditions under which the dinosaurs were living and the circumstances under which they became buried and fossilized.
All over the park, the life and death of the dinosaurs is engraved by the rivers here in the rock. An ancient flood left this thick white stripe of sand on the darker mud of the plain, and floods leave more than sand behind. At the contact between sand and mud, paleontologists look for fossils, the debris of a flooding river. Phil Curry finds a little heap of broken bones, all that's left of a baby dinosaur. Millions of years ago, rivers in flood swept up bones and living animals and carried them downstream. When the flood abated, they were deposited, often on a point bar where the flotsam of a river collects. Gathered over time, these bones became fossilized. Bone beds, the dismembered remains of hundreds of different animals, jumbled together by the river that brought them here.
One can easily see how the currents have affected the bone bed here, because the majority of the bones will align themselves parallel to the current that was running through the region 75 million years ago, or perpendicular to the current. And the best indicator we in fact have for direction of current are the vertebrae, because the vertebrae have a very heavy lower end and a light wing-like upper side that align themselves in the current such that they always point downstream.
Most bone beds are a random assembly of bones from animals that died elsewhere from a variety of causes. They shed light on the ecology of the area, the different species of animals that live together here. But this particular bone bed is different.
This bone bed is about half the size of a football field, and since 1979 we've excavated less than 20% of it. Yet in that 20% we've discovered more than 50 individual specimens of an animal called Centrosaurus. This was a large horned dinosaur looking very much like a rhinoceros.
In one bed, up to 300 animals of the same species. In such a large population, the variation in body and brain size can be studied, and the age distribution of the herd at the time of death can be established. This information helps to explain the mystery of how they got here. A great herd of centrosaurs lying together on a point bar in that long-lost delta.
This region would have looked very much like the southern part of the United States now, both climatically and environmentally. There were a large number of different sorts of forests and swamps and streams and so on. And the Centrosaurus, being a very large animal, probably would have been free to move across all of these microenvironments, seeking whatever food it liked. One would presume that a good explanation for the demise of the herd that we see here is that they were trying to cross a river in flood, and that many of the animals drowned there.
A catastrophe can be read from the bones of its victims. In this herd of African wildebeest, most of the animals are mature adults. In the natural course of events, it will be the vulnerable ones that die, the very young and the old. But catastrophe strikes strong and weak alike. In the midst of migration, many adult wildebeest die beside the weaker ones crossing the flooding river. Like the centrosaurs, these bones will show a range of ages close to that of the living herd. Heaped up on the point bar, their bodies wait for dissolution. A pattern of events is written here, the same events that happened in another river, one day 75 million years ago. Beneath the trees at sunset, two dryptosaurs perform a mating dance among the birds. Like us, the dinosaurs inhabited a complex world. To see them clearly, we must reconstruct that world, detail by detail, an art that's built on science. It starts with the solid facts of fossil dinosaurs. Eleanor Kish at the National Museum of Natural Sciences begins each of her dinosaur paintings by modeling the individual animals. The dinosaur grows out of the evidence, measurements of fossil skeletons, and studies of animals alive today. The bones are precisely modeled in papier-mâché. This work is the product of a close collaboration between Eleanor Kish and Dale Russell, curator of fossil vertebrates at the museum. The finished paintings will illustrate his books. In a scaled-down model, this is a tyrannosaur, the largest carnivore yet discovered. Its huge springy backbone is built to support a body that might have weighed 6 tons in life.
I've got to wrap this muscle around these bones.
Many fossil bones show where the muscles were attached. Like living animals today, they're designed for efficient movement and for support.
And then from this point on, it's a buildup of that muscle to get that to look proper. That's a strong muscle. And this would be heavy because he's on it. And this is just my observation of horses when they're in action, or cows when they're taking off to walk or run. This process keeps going until I get this roughed out over the entire thing, and then the other side's in 3 stages of finish, which I'll just turn that here. And I build it up until I get my muscles where I want it, like in here, then where my hollows are, and I give this the power that it needs to pull this leg around, and then I begin my finishing. See, I want his skin to give the appearance like an elephant, and I don't want to lose the shape, but I've got to get my little wrinkles in there.
The Tyrannosaur's prey is a duck-billed dinosaur. Fossil imprints of duck-billed skin have been found, and Eleanor Kish reproduces them here.
I love it when it starts to finish like this. The whole thing is to reach this point, and I get so excited I don't eat or see the time.
When it's finished, the abstractions of science have become a 3-dimensional reality. It's photographed and projected onto canvas, like a slideshow from a journey in time. Careful tracing makes sure that the painted version will reproduce the accuracy of the model's construction. Now the scene begins to take shape. It's blurred at first, but soon it will be a precisely realized moment, a split second in time, 66 million years ago. It has an exact location, too, beneath a fan palm in a salt lick environment. Here, a tyrannosaur ended its hunt and caught an unlucky duckbill. Patterns of light and shade reproduce the living tissue. Pulled by powerful muscles, the leg kicks up, ready to slash and tear the captured prey. This is a reality that we can recognize. For all the strangeness of the central figures, this scene is like the living world today. It's a picture of a past that's immensely distant, but it's painted from life. Some living things on this planet change very slowly. Many species of trees and plants go back a long way. Though their distribution has changed with the world's climate, the plants and their environments were much the same in the world the dinosaurs inhabited. 150 million years ago, a striped Tenontosaurus ate a cycadoid, close relation of the cycad of today. We know because one part of every plant is almost indestructible.
A flower has such a brief moment of splendor. A day or two, and its fragile beauty begins to fade and die. But all of this short-lived color and shape and scent is only packaging, designed to hitch a ride for some of the toughest, most durable cells in nature, pollen.
Think of the job a pollen grain has to do. Smaller than dust, it must get to the female portion of another flower. That may be equivalent to a trip to the moon for a human being. The journey's done on an insect's back, in the gut of a bird, or randomly in the wind. Rain or shine, it must survive the weather and arrive fit and able to fertilize. No wonder pollen's produced in such quantities, every grain built to last. Each species of plant designs its pollen to its own pattern. It's like a fingerprint. Seen under the microscope, it identifies the species. Hibiscus pollen is just large enough for individual grains to be seen with the naked eye. But when we look at the golden clusters under the microscope, we can see the characteristic shape of each grain, a spiky sphere. The scanning electron microscope shows the detail that makes hibiscus pollen and pollen and spores of every species recognizable. Fossil forms like these keep their fingerprints for millions of years. The pollen wall is a complex hydrocarbon that stands up to the assaults of time, as well as the torture tests devised by scientists. Pollen specialist David Jarzen of the National Museum of Natural Sciences crushes rock from Dinosaur Provincial Park, breaking the pollen from the matrix it has nestled in for 75 million years. Extracting the pollen from the rock dust requires something even stronger. Hydrochloric acid. It dissolves rock, but pollen, it just polishes up a bit. After a centrifuge has separated out the pollen, it's stained to make its structure easier to see under the microscope. This ancient pollen is easily recognizable. A reference collection of living species of plants provides the modern form for comparison. Given the time that separates them, it's a very close match. Under the scanning electron microscope, this is the fossil, and this, the modern pollen. It comes from a tropical plant that's flourishing today, pandanus, here seen in fruit. The pollen record in Dinosaur Provincial Park shows that dinosaurs walked through groves of pandanus trees. They browsed on maples and drank from pools covered with water lilies and the little water fern azolla. Other ferns left their spores by the millions in the sediment. We begin to build a complex environment. In the bald cypress swamps of that ancient delta, other animals besides dinosaurs lived. Some of them still inhabit this southern swamp today. The group this alligator belongs to, the crocodilians, have shown incredible staying power on the planet. The turtles were around when the dinosaurs were, and they're still here. Birds stalked on water plants in the dinosaurs' world too. They shared the air with flying reptiles, the pterosaurs, long since gone. Insects, other reptiles, and hidden in the trees, the mammals, small squirrel-like creatures. They evolved at the same time as the dinosaurs, but for millions of years, they had to play an evolutionary waiting game, with no chance to expand while the dinosaurs dominated the earth. Dinosaurs were reptiles with a difference. All of them were built with their legs vertically beneath their body. It's what classifies them as dinosaurs, and it's very efficient. They could outrun the other reptiles of their world, who sprawled like lizards. And they could support enormous weight on those vertical legs, evolving into giants or carrying massive armor. They became the largest and the fastest animals around. A world in its prime, when the earth, the sky, and the sea were filled with great reptiles. The day of the dinosaurs lasted over 100 million years, and then it ended. 65 million years ago, the dinosaurs disappeared. They didn't go alone into oblivion. The sky was emptied of flying reptiles, and the land lost many species of plants. In the sea, the marine reptiles went, and the ammonites, a shellfish that once swarmed in countless millions. Only fossils are left. What happened? Was it a slow decline or a sudden global catastrophe? There's so little evidence.
As you know, we only have about 6,000 skeletal fragments of dinosaurs to work with spread over the whole world. So we don't have large numbers of dinosaurs to work with. The numbers that we do have seem to show no evidence of a decline before they became extinct. Other organisms that became extinct, apparently in the same extinction event, and are more numerous, vanished very abruptly. So it would appear that the dinosaurs disappeared as a result of some kind of a catastrophe. What this catastrophe was is suggested by the presence of elements in extraterrestrial abundances that were deposited at exactly the same time the extinctions took place. There have been various hypotheses offered to explain these extinctions, and the most current one is, of course, a planetesimal impact.
For some scientists, like Dale Russell, this was the end of the dinosaurs' world. A giant asteroid, perhaps 10 kilometers across, hit the Earth in mid-Pacific. Steam and debris from the impact shot into the air and formed a dense cloud around the planet. Months of darkness would cause a total ecological breakdown, and much of the life on Earth would start to die. But the verdict isn't in yet. Many scientists are unconvinced, and the final end of the dinosaurs still remains to be seen. For whatever reasons, the dinosaurs have gone forever, and today the swamp echoes with different sounds. But what a tragedy that all that incredible diversity, that vitality that evolved and changed and dominated the planet for 150 million years have disappeared. But are they really all gone? Or do they still exist, only hidden in a new disguise? Birds, shaped for the air, riding the wind. What have they to do with dinosaurs? More than a century ago, when paleontology was just beginning, anatomical similarities were noticed between birds and the carnivorous dinosaurs. The connection seemed absurd, though small feathered reptiles had been found as fossils. Today, with more fossil evidence, close analysis suggests that birds evolved from small, agile dinosaurs that developed feathers for insulation, the feathers that eventually allowed them to fly. Some birds are more like dinosaurs than others. Some flightless birds, like the ostrich, retain more primitive features in their anatomy than birds that fly. The ankle bones of flightless birds preserve a record of their descent from dinosaurs, evidence of a very ancient pedigree. The ostrich, the emu, the cassowary, they may have branched off the evolutionary tree at a very early stage in the development of birds. Chris McGowan at the Royal Ontario Museum is studying the descent of birds from dinosaurs. The evidence can only be seen in embryos because after hatching, many of the smaller bones in a bird's skeleton fuse together. In this ostrich embryo, the separate elements are distinct. The bones, stained pink, are replacing cartilage, the blue areas. In the ankle area, a small vertical flange projects upwards onto the shin bone. This bony feature exists only in bird embryos and in the ankles of carnivorous dinosaurs. The race of dinosaurs continues out of a past incredibly distant into the living world of today. As we fit together the pieces of the puzzle, the view from where we are begins to change. From the dinosaurs, we learn about another world that once lived and grew and flourished without us. The dinosaurs dominated that world for over 100 million years. Compared with them, we're a flash in the pan. But they did die out. If it really was a sudden and massive change in the environment that wiped them out, that should make us think. Our species may not have been around for long, yet already we've had an enormous impact on the planet. But if we do disappear, like the dinosaurs, what happens next? Is there another small creature hiding in holes, clinging to grasses, waiting for its turn? Or will the descendants of the dinosaurs be the next survivors? More than anything else, the dinosaurs show us about the incredible power of life itself, moving through 1 million different forms, meeting challenge and crisis, and surviving.